Hello, and welcome to the Homeland Defense and Security Information Analysis Center webinar titled The Science and Technology of Radiation Detection. My name is Steve Rutherford, and I'm the director of the HDIAC, and today we have the privilege of hosting Mr. Kerry O'Connell for this presentation. I'd like to thank our sponsor, the Defense Technical Information Center. The DTIC-IAC mission is to collect, synthesize, produce, and disseminate scientific and technical information to the DoD and federal government users, and this webinar is made possible through DTIC sponsorship. I'd also like to thank all of you for taking time out to join us today during these challenging times. So a few housekeeping notes as we start out. Please note that all lines have been muted. If you have questions during the webinar, they can be submitted using the attendee chat box on the left-hand side of the screen in any meeting. They can also be submitted via our streaming services. We will work to save the last 10 minutes or so of the presentation to go over these questions and discuss them. If we run out of time, we'll make a note of all the remaining questions and post responses after the conclusion of the brief. Please also note that this webinar is being recorded. A link for the recording as well as the slides will be available at our website, www.hdIAC.org, for later download. With that, it is my pleasure to introduce you to today's presenter, Mr. Kerry O'Connell. Kerry is the Senior Training Manager, CBRNE HAZMAT, at one of our HDIAC teammates, the Guardian Centers of Georgia. Kerry has more than 20 years of chemical, biological, radiological, nuclear, and high-yield explosive defense and emergency management experience. He served over 20 years in the United States Marine Corps, retiring as a Chief Warrant Officer 3. During his time in the Marine Corps, Kerry filled the role as CBRNE Defense Officer in multiple units, including an assignment to the United States Marine Corps' Chemical Biological Incident Response Force, where I had the great good fortune to serve with him. He also worked with the Charles County Tactical Response Team, and he has ample experience in the coordination of emergency management and CBRNE incidents. In his current role at Guardian Centers, Kerry has the responsibility for designing, constructing, and implementing innovative and realistic training scenarios at both the Guardian Centers Georgia complex and at various locations throughout the world. With that, the floor is yours, Kerry.
Thank you, Steve. I appreciate it. And I'd first like to start by thanking yourself and your entire staff at HDIAC. You guys have done an impeccable job in getting this all set up. And I just want to let you know on behalf of Guardian Centers, we really appreciate it. So to start off, we're going to talk about the science and technology of radiation. We're going to go over some basic terminology. We're going to talk about some specific isotopes, kind of get you guys to understand the difference between REM and Rankine. And then we're going to go into some of the detection capabilities that we have, as well as what happens when we have to respond and we have to go through the decon process. So without further ado, we'll start with some basic terms that we're going to go over. Some of these may be familiar to some of you, and some of them may not be. So we're going to go over these just real quickly so everyone's on the same playing field as we go through this brief. So the first couple, so we have Rankine equivalent man, or REM. Most of us in the radiation field or have dealt with detection equipment know what REM is. So we have RAD below that. So the difference between REM and RAD is because they are equivalent. 1 R equals 1 R, 1 REM equals 1 RAD. What the main difference is RAD is a measurement of the radiation that's absorbed by a material or tissue, whereas REM is that measurement, but it's the biological effects that it has when it's absorbed into your body. So a lot of the detection equipment we have, you'll see the word REM on that. So because we want to know what the dose is for us. And then we have Sievert. Sievert is SI, or what's known as the international standard. So it's comparable to REM. It's kind of like miles per hour and kilometers per hour. So the international standard would be Sievert. And the equivalent for that is 1 Sievert equals 100 REM. Same as for gray. So that's the international standard. So gray is equivalent to rad. And the same thing, 1 gray equals 100 rad. Next we have Curie. For people that are radiation safety officers or that deal with radiation a lot, we use Curie because that's the activity. That's the activity of that actual isotope. And each isotope is going to have, if it's a 1 Curie of cesium or 1 Curie of cobalt, it's going to have those becquerels. Becquerels are just a disintegration. So if I have 1 curie of an isotope, it's going through 37 billion disintegrations per second. All right. Now we see that we have the disintegrations per second, and right below that is the counts per second. Now we know when we talk about counts per second, we're dealing with contamination, and we have a meter that does counts per second. So you would think that counts per second equal the disintegrations per second. But they actually don't, because our meters cannot pick up every single disintegration that isotope is giving off. So we'll talk about that further when we get into the meters, because each meter has to get calibrated, and it's an efficiency factor. Next, we have exposure. So you can be exposed to radiation and not be contaminated. That's when we talk about the X-rays and gamma rays. That's the only thing that we talk about when we talk about radiation exposure. And the final one right here for that is electron volts. So electron volts are the energy of that radiation. 1 electron volt is very, very minute. So when we talk in the radiation field, we talk in keV and meV, which are kilo electron volts and mega electron volts. And as we go through a couple isotopes, you'll see that the electron volts go up significantly depending on what that isotope is. So near and dear to my heart is ALARA, as low as reasonably achievable. We do a lot of radiological training down here, and I want to make sure that I receive the minimal dose that I can while I'm doing training. And the way to do that is we use time, distance, and shielding. So stay time. If I have a source that's 10 R per hour, I have to be there an entire hour for it to reach 10 R. We want to get in and out as fast as possible to reduce the amount of absorbed dose that we're receiving. Next one is distance. So we use what's called the inverse square law, and this will be described on the next slide. But the further away you are from a source, the lower the readings are going to be on your meter, as well as the less of the absorbed dose you're going to receive. And then shielding. We want to use materials that are dense. If we put them in between us and the source, it's going to lower the absorbed dose that we actually receive. So here we go with the inverse square law. It's rather simple. If I'm 10 feet away from a source and it's reading 1 R, if I go half the distance in, the activity is going to go up by 4 times. So if I'm reading 10 R at 10 feet, or I'm reading 1 R at 10 feet, if I go to 5 feet, it's going to be 4. And then if I go from 5 feet to 2.5 feet, it's going to go from 4 multiplied by another 4, 16. So as you can see, the closer we get, the higher the activity is going to be, and then the further away we get, the lower it's going to be. We don't want to have to go up to a source if we don't have to, so we can use this inverse square law if we know it's a point source, and we can find out actually the activity of that source and the dose rate that we're going to receive. All right, and then we talk about half-life. So every isotope has a half-life. And the half-life is the time for that source to lose half of its strength, or what we call activity. On the right, you can see we have cobalt-60. Cobalt-60 has a half-life of 5.27 years. So in 5.27 years, if it started at 10 grams, now it's going to go down to 5. And then as we see, divides by 2.5. So it takes some time depending on the isotope. Some isotopes are very short-living, milliseconds, nanoseconds, picoseconds, while others can be billions of years. All right. So let's get some dose understanding. So we talked about REM. That's the biological effects that it's going to have on your body when it gets introduced to your cells and mutates your cells. Well, 1 REM is actually a lot unless you work around a nuclear facility and you have to go in where the rods are and you're doing that type of work. But for normal people just doing training, 1 R is a significant amount. But what our meters do is they break that down, and we can go down to the thousands, which would be millirem, or we can do micro rem. So that's the millions. Give you an example, background, which is the normal radiation that's around us any given day, in most areas is going to range between 3 and 30 microrem. So if you see, I kind of did the calculation, 30 microrem is really 0.00003 R. So it's really not a lot. And then we have counts per minute. So counts per minute, we're going to use that when we're talking about contamination. And as you can see, I did 2 of the equations. So cobalt-60 is 1,080 counts per minute is about 1 millirem, where cesium-137 is about 1,200 counts per minute. And the reason that cesium or cobalt-160 or cobalt-60 is lower is because it has a higher what we call MEV, the mega electron volt. It has a higher mega electron volts and actually has 2 compared to cesium. So it's actually, even though 1 curie of cobalt 60 and 1 curie of cesium 137 are both 1 curie, one is going to have a significant more energy than the other. And then my note for background radiation can fluctuate. If you go into Penn Station or anything that has a lot of granite, your background's going to go up because of all the uranium and radium that's in the soil and in the rocks. There are some instances and places and beaches in the world where you could be at 1 or 2 MR, which is, what is that, 100 times normal background. All right. So here we go with dose limits. So this is for a radiation worker right here. So occupational dose, I'm allowed to receive 5R per year. That's my whole body. When we talk whole body, we're talking about the chest area, okay? That's where I'm gonna have my TLD at. That is the main focal area that we're concerned about when we're talking about radiation. As you can see with the lens of the eye, I can get 3 times as much because the lens of the eye, I don't have cells that are generating rather quickly. And that's what we talk about when we talk about how the biological effect's going to happen on your body, is how fast your cells regenerate. Those cells that regenerate rather quickly are going to have a significant more impact on your biological effects, where some that don't produce quickly or at all, let's just say nerve cells, they're not going to be susceptible to the biological effects of radiation as much. And then we see skin and extremity is 50R. So we don't have too much there that we're concerned about as much, so we can get up to 50R. Pregnancy dose, you're allowed to get 500 millirem during the whole gestation of the pregnancy and up to 50 MR per month. Now, when we talk about the public, you can see the dose is a lot lower. It's 100 millirem per year, and we have the 2 millirem in any 1 hour. Now, that's important to me because when we do training and we have role players, we actually have to graph out after we place the sources to find that 2 MR line. We need to make sure that those role players are outside of that. Of course, we use ALARA, so we try to get them much further away from that because we want to limit the amount of dose that they receive while they're here. And then we can see in the emergency dose limits, so 5R is the standard. We can go up to 10R if we're protecting valuable property. And then for life-saving, 25R. Anything above 25R, it has to be known to the volunteer what they are possibly going to expect for later on in life if they go back into the hot zone. And then here are some examples. Again, we start with 5R, which is the annual safety limit. So 50R over time associated with bladder, breast, colon, liver, lung, stomach. As you can see, the majority of all of those are what we're talking about, that whole body, where your chest and all of your organs are. 70R for an instant radiation exposure will cause vomiting. And then as we get up higher, 350 to 500, you're going to have that LD 50-30. That's where the percentage of you dying is, the lethal dose is 50% of the population dying within 30 days. And then we have 1000R, which is internal bleeding, the destruction of the intestinal lining, and more than likely death within 2 weeks. And that final one, as you can see, that's the dose exposure that the workers and firemen at Chernobyl got in 1986. And actually, this past Sunday was the 34th anniversary of Chernobyl. It happened on April 26, 1986. All right, so now let's kind of get into the science of radiation. So as you can see on the periodic table that we have here, I have oxygen. So oxygen is what we call a stable element. You see the number 8 there, that's the atomic number. So I know oxygen is the 8th element in the periodic table, which means it has 8 protons. The atomic mass to the right, the 15.99, that is how many protons, neutrons, and the weight of those. So we know neutrons and protons are almost about the same weight. So I know that that has 8 protons and 8 neutrons. We always know if it has 8 protons, it's going to have 8 electrons around it. So this is what we call a stable atom. Here's another example with carbon. So I have 6 protons, I have 6 neutrons, and then I have 6 electrons. And every electron field there, first one has 2, second one has 4, and then it goes up as we go forward with higher elements in the periodic table. So types of ionizing radiation. So the main ones that we're going to talk about, well, we're going to talk about them all. So we have alpha, beta, and neutron. Those are our particles. Those are the ones that are going to be on us. We don't want to inhale, especially alpha and beta. Neutron's a little faster, and we'll discuss that. And then we have the electromagnetic waves, the gamma and the X-rays. So these are the 5 that we're going to be discussing. So the first one's an alpha particle. So those of you that understand the periodic table know if you look at that alpha particle, all it really is a helium atom without the electrons. So what happens is you have an unstable atom, and it has too many neutrons, and it wants to become stable. What it does is it pushes off that alpha particle, which is 2 protons and 2 neutrons. Now, it doesn't go too far because alpha particles are big in relevance to radiation. So they can be stopped by skin, they can be stopped by paper. Our main concern with alpha particles is inhalation. And then we have beta. Beta particles are a little smaller. It's pretty much an electron, but it can work in 2 ways. So for a beta particle to actually go off the isotope, what happens is you have beta minus and you have beta plus. So minus is when the neutron converts to a proton, and then it creates that electron. The other process is the proton is converted to a neutron, and it creates a positron. So positron is pretty much an electron, but it has a positive charge. Next, we have gamma radiation. So gamma radiation is not a particle. It is a wave. So what happens is that atom is unstable, but it's not pushing anything off. Now, there are a lot of gamma-emitting isotopes, but they also emit some low beta or low alpha, depending on what they are. For the most part, the main energy is going to be from that unstable atom that's giving off the gamma rays. And they can travel a lot farther than alpha and beta. Gamma rays can travel 100, 200 feet, depending on the activity of that actual source. And then we have neutrons. Neutrons are very small, they're very fast, and they can actually, what we call indirectly ionize another atom. So they can absorb themselves into a stable atom, and they can increase the probability for that atom to become unstable, so it can actually make another atom emit radiation. And we're going to talk about some special equipment that is used in the radiation field to actually get the correct dose of neutrons. But mainly neutrons are going to be coming, when you see neutrons, mainly it's because it's special nuclear material. That's the majority of where we're going to find those neutron particles. And then we have X-rays. So X-rays and gamma rays are somewhat the same. X-rays have a longer wavelength. That's why they're not as damaging as gamma rays. Also, in gamma, the ray actually comes from the nucleus of the atom, whereas in the X-ray, a neutron bombards, so this is tungsten. So tungsten's the 74th element. Tungsten is one of the main ones that's used in X-rays. So they'll bombard it with a neutron. That neutron actually pushes an electron from the lower shell off. When that happens, an electron from the outer shell wants to replace it. When this occurs, you have that X-ray radiation that goes off. And then here we have our shielding. So with our shielding, as you can see, alpha can be stopped by paper, can be stopped by your skin, clothes that you're wearing. Beta can go through a little further, maybe like a centimeter into your skin, possibly, depending on the activity. So we talk about, we hear beta burn, but like I said, the alpha and beta, the main ones that we're concerned about is that inhalation hazard. And then gamma can be stopped by lead. The more you have, the better. If I have an inch of lead and I have a high activity source, it's going to lower it, but it's not going to completely stop it. But it will shield you from a lot of the rays that are going through. And then X-rays are the same thing, go through lead. Now neutrons, a lot smaller, a lot faster, usually stopped by water, polyethylene or plastics. Just, you can kind of see, if you go on YouTube, you can see videos of nuclear power plants, and they're submerged in water, and when they pull out the rods and it gets really bright blue, water is good for shielding neutrons, as is plastic. All right, so what we're going to do now is we're going to go over a couple of these elements. A lot of these that we use here, and of course we're not using any special nuclear material, but We're just going to go through these so you can kind of see the difference where they're processed, if they're man-made or if they're in the earth, and how they affect us. So the first one is americium-241. For those of you who don't know, you all have americium-241 in your house for the most part if you have a smoke detector. Americium-241 is used because you have the negative and positive ions. If smoke goes through that, it halts the process and slows it down, and that's when your smoke detector actually goes off. But americium-241, if we look at the decay energy, that's what we're focusing on. So we have a 5.4 mega electron volts. That is a significant amount for alpha. And as you can see, it has a low gamma. So even though it is main emitter is alpha, it does have some gamma. So as we can see here, it's used in the industrial, medical, commercial fields, can be metal or plastic discs. And as we talked about, main thing is inhalation or swallowed because it can stay in your system for a long time, mainly in the bones, liver. Next one is cesium-137. That has a beta minus energy and also gamma. As we can see, gamma is the higher of the two energies. So its main emitter is gamma. And then when it decays to barium-137 is when we get our beta. Again, most of these you're going to see are metal. So you have a gray or blue metal, kind of looks like nickel. Cesium-137 is probably one of the main calibration isotopes that's used when we do our calibration on our detectors and also on those radiation therapy devices. So what's bad about cesium-137 is it reacts into water in our body. It has a biological half-life of 70 days, which means once absorbed into the body, it's going to stay there for 70 days. But we do have medication like Prussian blue, so we can reduce that 70-day biological half-life to about 30 days. Next, we have cobalt-60. As I was talking about before with cobalt having the 2 gamma, so we see the energy, we have beta 0.317. So it has a low beta, but it has 2 gamma emitters. So we add those both up, and now we're talking 2.3. So cobalt-60 compared to cesium-137 is significantly more energy. Also, solid metal comes in metal discs. It can be used as a fine powder. It's usually used for radiation therapy. They put it in leveling gauges, so they'll X-ray welding seams. A lot of construction workers, you'll see a yellow box. They actually use that to check for any places in the ground that are not solid. And then we talk about the external exposure. So large sources of cobalt can cause skin burn, acute radiation sickness. Most is excreted in the feces, but it can be absorbed in the liver and kidneys. Again, that whole body area we were talking about. And then iodine-131. This is the one that our body doesn't know what it is, but that can be kind of a good thing. So iodine-131, as you can see, it's mainly going to be a beta emitter. It does have some gamma. But what's cool about iodine-131 is when we take iodine into our body, 95 to 99% of that goes to our thyroid. So for people who have thyroid cancer, they actually use iodine-131 because our bodies cannot distinguish from stable and ionizing iodine. So that's really good for helping with thyroid cancer. Next, we have plutonium-238. As we know, this is almost strictly alpha. It has very minimal gamma at all, strictly going to be alpha. So it's created from the uranium in the nuclear reactors. And then, of course, we're going to have the byproducts during the nuclear weapons production and the nuclear power operations. Solid metal, again, under normal conditions. It can be used it does generate a lot of heat, so it can be used as a heat source. So if you have satellites, if you have beacons or any retrans for communications, it's a good one to use. And as we see again, with something being alpha, our main concern is that inhalation or ingestion. Next, we have polonium-210. Polonium-210 is probably one of the top 5 most toxic substances on Earth. Now, if you look at the energy, the alpha is 5.4. The half-life is very short. It's about 138 days. and it's in the decay chain of uranium and of radium. So uranium-238 will decay to radium-226, and then it goes to radon-222, and as it goes down, it's going to go to polonium-210. So solid metal, used in the industry for devices to remove static. So they'll actually put some of these in products like computer chips so that keeps them free of dust. And as I said, it says here, 1 gram of polonium-210 is enough to kill 50 million people. And for those of you that don't know, Alexander Litvinenko was a British naturalized Russian. So in 2006, he was actually in a meeting and they poisoned his tea in the hotel with polonium-210. And within 22 days, he had died. So it's some pretty nasty stuff. And then we have strontium-90. So strontium-90, mainly going to be a beta emitter, 0.546 MeV. So it's produced through nuclear fission. It's used in the medical industry. Soft, shiny silver. They use strontium-90 a lot when they're putting them just like they're putting them in the beacons as well. So strontium-90 can get very hot as well, depending on the activity. What we're concerned about the most here, of course, is ingestion. And then that's going to be in your teeth and your bones. Next, we have uranium-235. So uranium-235 occurs naturally. It can be enriched, and that's when they do that for the nuclear reactors. Main emitter there is going to be alpha. It's very dense, and it's used for fuel in the nuclear power plants. Can cause significant lung cancer if inhaled. And the next one, uranium-238. So we have the same concerns here, but what's different about this is when we start talking about depleted uranium. Everyone's always heard the term depleted uranium. So uranium-238 and 235 kind of go hand in hand, but what we want to do is we have little amounts of uranium-235 that's going to be better for making that depleted uranium. So depleted uranium contains mostly uranium-238, and that's going to be used for shielding and, of course, as we know, armor-piercing weapons. But depleted uranium is very dense and it's used great for shielding. All right, so now we're going to talk about some dosimeters and some detectors that we use. So the first one is what we call a TLD, a thermoluminescent dosimeter. And as you can see, I have mine there, and then I have a different one left. So I wear this, and this is going to give me my whole body dose. Every time that I go out to the bunker and pull sources or do leak tests, I'm going to have this on me. And for our company, this one, as you can see, is from April 1st to June 30th. So I have three months. I get a new one every quarter. I ship that off, and they record the dose, and they keep that dose. So every quarter I get a new dose. At the end of that, I get my accumulated dose. So it's always accumulating my dose, and they're going to keep those records for 50 years. And the reason why is if I'm 40 years old and I decide, hey, I don't deal with radiation anymore, 10 years down the road, if I want a job doing that, they're going to want my records. So it's good that they keep the records for 50 years. And the one on the right will do gamma, X-ray, beta, and or neutron radiation. The one on the left is the one that we actually give to our students that don't do TLDs. So that one can actually be reset, handed to a student, and then before he leaves training, I can read it on my Bluetooth. I can print them out a report, I can clear it out, and I can give it to the next student, which is, it's good to give people their doses before they leave for training. So we enjoy using those. And then there's my extremity dosimeter. As we talked about, my extremities, I can get 15R. So that's the ring that I wear when I'm handling the sources, when I have to go into the lead pig or grab a lead pig that has sources. And these can be worn for 1 week up to 6 months, but I keep that on schedule with my quarterly TLD. And again, that'll keep your lifetime dose for 50 years. And that reads low or high energy beta, X-ray, and gamma. Next, we have EPD. So not really used for, you don't want to really use it for detection, but what I like about the electronic personal dosimeter is with the TLD, it can't tell you what you currently have. The one that is here, I think that's a Tricerco, but as you can see, the top, that 1.8, that's the highest peak rate that that individual got. And then you see the dose. So the dose is 3.19 microsieverts. That's how much accumulated dose that they've received. And then that bottom left one is their current rate. And as it goes up, that state time where it says 996 will actually tell you how long that you have. So EPDs are good to use if you don't have any other type of detection equipment, but I wouldn't specifically use it just to detect radiation. Oh, I think I went too far. And then we have our PRDs. So as we know, if we're an element that's going to a radiological response, we don't have enough detectors to give to everyone that goes downrange. So the PRDs are good for those personnel that don't have them. They've already been cleared to go in an area where they know the rate is below whatever the incident commander has stated, but it kind of gives them a feel good to know what their current dose rate is when they go down. And they're small. They have audio visual alarms. You can set them to whatever you want. And then we have our handheld survey meters. As you can see, that top one is a DSM 525. They come with different probes, and then you can see the bottom, the person that's in mop gear, he has an AMPDR 77 with a pancake probe. So as we can see, we're using the pancake probe because he's checking contamination. So he's checking in counts per second or counts per minute. And these are great to use because you can switch out your probes. If you don't know if you're dealing with alpha, beta, or gamma, you can mix and match. If you have three, you can have one that has the beta gamma on it, and you can have another one that has the pancake probe so you can check for contamination while you're also checking for your dose. Next, what we have is the RID. So the one on here is Identifinder. It's a great piece of gear. It actually has a sodium iodide crystal in it. It's able to not only detect radiation, but it can also identify. Now, when we talk about identify, it cannot detect alpha or beta, but it can identify it. A lot of people were kind of confused in our last class that I had down here, and they said, well, how can I identify it if it's an alpha? Well, what it does is it uses the spectrum, so the gamma spectrum. And as we saw with americium, it does have a small gamma. I think it was 0.05 but what it does is it uses that gamma spectrum and it can tell that it's americium. So while it can't detect alpha, it can identify off of that gamma spectrum that it is alpha. But it comes with a set library. It'll tell you if it's an industrial isotope, if it's special nuclear material, medical, there's a couple others. And what's great about when it identifies it is it's going to give you a number, what the source is, and then, so perfect example would be if I had a large americium 241 source. It would identify it and it would say 9 AM241 IND. And it's saying that, hey, 0 to 10, I'm saying it's a 9 out of 10 that I am certain. So that's what's good, because if we identify something it's a 4, we're kind of unsure. And then we have our neutron detector, or what we call a REM ball. So the identifier can detect neutron. It can give you counts per second, but it's not as accurate as a REM ball, because what the identifier isn't doing is it's not blocking the gamma rays. Now, there are many different types of neutron detectors, but one of the ones that we can do is we can measure slow or fast neutrons, and it depends on that plastic cylinder. As we talked about, polyethylene is going to be great at stopping or slowing down neutrons. And as I talked about, neutrons are super fast, so we need something to slow them down. So that ball on the bottom is actually slowing down the neutrons so we can get an accurate reading of what the actual dose rate is. And as I said, it uses gamma rejection for that accurate measure. And then there's many different types. If you just want to measure slow neutrons, if you want to measure fast neutrons, they make them all for specific types of industries. So decon principles and techniques. Whenever we do training with people, we always talk about, is it loose or is it fixed? We're probably never going to get every single particle off of a person coming out. But the question is, are they a concern to anyone else or just themselves? So what I'm talking about with loose versus fixed contamination, for those of you who don't know, if I have a casualty coming up to me and I have my pancake probe and I check and say on his arm, I'm getting elevated readings. Well, what we do is, depending if we're using wet or dry decon, is I would swipe that area. Now what I want to do is I want to check his skin. Is that reading gone down or gone up? Well, it's gone down. Okay, well, let me check my rag. Is my rag going up? Yes. So I've removed it, which means it's loose contamination. You could get to the point where you rubbed it all off and he's still irradiated, but you're not getting any readings on your rag or whatever you're using to remove that. That means that it's fixed. And if it's fixed, it's not coming off. Now we need to make a decision, depending on who the IC is, if we're going to allow that person to stay in the warm, or make him stay in him or her in the warm zone, or we're going to let them out because they're only a concern to themselves. And people who don't know, your skin cells regenerate and regrow about every 27 days. So depending on how high the activity is on that, we could possibly make the decision that they're not going to be a harm to anyone else. And maybe we just kind of put them off to a side, let people know this area is going to be for people that are contaminated, but it's fixed. We can't get any more off. So decon principles, wet versus dry. When are we going to use them? Well, it's all going to be dependent on the gear that we have and do we have enough of it? Are we dealing with mass casualty radiological response, or are we dealing with something small? So which method is going to be the best? So how many casualties, as I said, we have the resources, and is it cold out? If it's negative 32 degrees, I don't know if we're wanting to use water, because now I don't think radiation's going to be our highest priority for people getting injured. It's probably going to be hypothermia. So here's some of the special considerations. So wet decon. So if we have a tent and we are deconning personnel, every person that comes through, we're dropping that radiation into the water. The water staying in the pit. Every additional person that we receive, that pit is going to get hotter and hotter. The activity, the energy in that pit. So we just need to consider, if we're going to be using water, where's that water going to be? Do we have a means to take the water away from our first responders that are deconning? Can we pump it out back into a 55-gallon drum or something back into the hot zone, so we're limiting the dose that our first responders are receiving? And then dry decon. If we're talking mass casualty, do we have enough rags? Do we have enough whatever we want to use to do physical removal? But we just got to remember, when casualties come up to us, 90% of that contamination is going to be on their clothing. The easiest way to reduce the amount of contamination coming to your decon area is going to be having that area prior to where they reduce their contamination by taking off their outer layer of clothes. And then, as we know, alpha beta particles, they're very small. So if you're wearing PPE that has seams, it could be harder to decontaminate. And depending on how long you're doing your swap out of decon personnel, you may have to do your considerations for your logistics on how many suits am I going to need? How many gloves am I going to need? And we always plan for the worst and we hope for the best. All right, so next thing we're going to do here is I'm going to show you a video, quick backstory while this gets loaded. So back in 2001 in Leah, Georgia, which was the former USSR, there were 3 people that went into the woods to go and collect firewood. They found 2 metal objects, and we call them orphan sources. So they were left behind, and you wouldn't even imagine how many other sources that they found in this area since this video. But what they decided to do is they said, hey, we see these metal objects, they're kind of hot. let's use them as a heating source while we stay in the woods overnight. Now, maybe asking yourself, like, what are the two metal boxes doing in the middle of the woods? But like I said, they were used for something, and what they ended up figuring out is the two metal boxes served as a radio relay system between two of the hydroelectric stations there. So a place where you don't have any electricity, this is where we start using radiological isotopes. So these two sources were part of a network for a relay system, so those two hydroelectric stations could talk. Now, the actual people that were around the two sources ended up going to the hospital about 2 weeks later, and at the end of the video, you'll see, just quick warning, you'll see that they actually have bandages on them and they pull them off and their skin's kind of loose from all the beta that they've received. So I'm kind of gonna fast forward through some of this. I just want you to see some of the things that we discussed earlier. So the first thing that they need to do is they need to gather a team together. So, well, shielding. So we're gonna talk about the time, distance, and shielding. So there's their shielding. That is a significant amount of lead. That should definitely do the trick on shielding those two sources. And then we're going to train. I always talk about when we're going down and we're responding to something, is time a priority? We always ask, hey, how much time do you need until we go down range? If you can practice in the cold zone, you absolutely want to do it. And as you can see here, they're also using distance. So they built their shielding, he's using distance, and they're actually using time as well. Once we get further on, you'll hear they'll actually start blowing the whistle. They only have a certain period of time. I think it's anywhere from like 45 seconds to a minute that they're allowed to be around the source. So they know what it looks like. They're using the same equipment they would. They kind of placed it how they thought it would be. And they're going to practice before they go out there, because the two strontium-90 sources that are out there are significantly high activity. Now, as you can see, that kind of went pretty smooth. Let's see what happens when they do it for real. I'm going to kind of fast forward through this here to get to them driving up.
So I've now going to go.
Here we go.
No.
So here's the first guy coming in. And you'll hear the whistle. I don't know if it's this person or not, but he gets about 45 seconds or a minute to be around that source, and they're using their distance to pull it out.
Have to clean the snow. Yeah.
Oh, we don't know, good.
25 seconds. What time he goes, isn't it? 30 seconds. Oh, that's okay.
And there's his whistle. So they've come to an equation where they said, all right, at 1 minute, this is the max dose that we want you to receive. So they did the calculations to figure out that it was going to be a minute.
It's possible to... Oh, he's going to try and hook it up. He's getting very close. He's very close. See the smoke coming. Come out with it.
And then you can hear the Geiger counter in the background as he pulled that out.
Fantastic. 25 seconds. 400.
Now, I'm going to fast forward a little bit here because they're going to get the second one, but as I talked about earlier, when we talk about radiation, you always hear the word hot, if the source is hot. But all the sources I've ever seen, they're not any different temperature than what's around us, because we're dealing with lower activity than something like the strontium 90. But as you'll see with this second source here, as they pull it out, it's actually steaming. The radiological source is so hot that it's actually melting and steaming the snow as they're pulling it out.
Yeah.
처음에 바로 들어.
And then they're just going to do the same thing. They're going to put it in there. I'll kind of fast forward so you guys can see the actual patients. So this is January 30th, so this is about 2 months after this actually happened. And as we use the term beta burn, this is exactly kind of what we're talking about here. All right, so Steve, that's all I have. I wasn't sure if you wanted to discuss any of the questions.
So, hey, Kerry, thank you very much for that presentation. We did have a couple questions come in, and just a reminder to everyone, we have about 10 minutes left in this presentation. If you have any questions, you can just drop them into the attendee chat, and we'll pick up on those. So, Kerry, one, and some of them got answered, but I'll go ahead and bring them up from the group in case, because, for example, our folks that are streaming it can't see the questions. So the first question James Miska asked, is polonium-210 toxicity primarily due to radiological or chemical?
So polonium-210 can actually go through what we call sublimation. So polonium-210 can go from a solid to the gas phase. But the main thing is, yes, that chemical, it's going to be both that chemical and the isotopes reaction that is going to affect that person.
So, but again, what you're saying is that it's the radiation, though, essentially, that was the primary source of the toxicity in those cases.
Right. So I know when people hear the word toxicity, they think about chemicals. I'm just saying, if I talk about the most deadliest things on Earth that are chem, bio, rad, nuke, I would say polonium-210 is in the top 5. So when I talk about toxicity, because what ends up happening is those alpha particles will go and they mutate a cell. So those cells that regenerate, what ends up happening is it breaks the chain in that DNA. Once the chain's broken, that DNA in the cell mutates. Now we have a mutated cell. What causes cancer cells is that mutated cell starts dividing as well. And as it divides, it's still mutating. And it doesn't work like a normal cell when it says, hey, I know I only have this long to live. It'll keep living and mutating. And that's where we start getting our cancer cells from.
Okay. So Michael Patterson asked about the limit of detections for most handheld meters. Angela jumped up and commented, I think it's a very good point and something I know we used to do at CBRF, that the manufacturers of the instrument can actually provide an awful lot of information about their instrument. But in your experience, Kerry, what is the limit of detection for most of the handheld sensors that are in use?
So for limited detection, I would say neutron for what the military has is definitely getting that exact reading from neutron. A lot of the new detection instruments that are coming out on the market here shortly can actually distinguish between them. So you could actually have one detector that can tell you I'm reading this for alpha, this for beta, and this for gamma. I know the one that's possibly taking the place of the AMPDR77 can do that. I actually have my hands on it. It's a good piece of gear. But I think what I wanted to let people know about the efficiency of the meter. So a lot of people think if I'm reading 1,000 counts per minute on my meter and the identifier is set at cesium-137, it actually isn't reading 1,000. So what we end up doing is we have our meters and they get calibrated. They'll come back and we'll use cesium-137 because a lot of the instruments are calibrated with that. So cesium-137 is calibrated to the instrument. They will have a known activity source, and we will just say that that source is 1,000 counts per minute. So we know with our laboratory equipment, we have 1,000 counts per minute. Now I'm going to put that AMPDR77 or any detector at the same location, and I'm going to see what that's reading. If it only reads 200 counts per minute, that means that it's 20% efficient. No meter is going to be 40, 50, 60% efficient. Almost every one of the meters that we have, depending on the isotope, is going to be anywhere from 10 to 20% efficient. And we just need to do our calculation, which is pretty easy. All it is your counts divided by your percentage, and that actually equals your disintegrations per second or per minute.
Super, thanks, Kerry. So here's a kind of a personal question. Lloyd Wallace wants to know if you've ever been able to visit Chernobyl during or after the event. I think any similar event, Fukushima as an example might be a good one. He asked, if so, what stands out in your memory?
I have not, but it is on my bucket list, and I actually talked to my wife about it. So yeah, I definitely would love to go to Chernobyl. It's very intriguing. I actually enjoy watching the miniseries on Chernobyl, but it's definitely on my bucket list. So I hope to get there.
So Lloyd also followed up. He goes, are there training areas available in areas where incidents have happened where DoD civilians would be able to have access? I think you might be able to talk a little bit about certainly what you do down there at Guardian Centers with live sources. That might be useful.
Yeah, I don't know if there's any places like Bikini Island or any places that you can go to, because I know most of those now belong to federal, and the access is pretty much TSSCI type stuff. But yeah, what you were talking about with down here. So at Guardian Centers, we have probably 170 different sources here. We have cobalt-60, we have cesium-137, we have americium, we have strontium-90, we have a neutron source, which we call AMBI, which is americium and beryllium together. And then for people who do a lot of radiological training, we actually do what's called loose contamination, advanced radiological contamination. That's where we actually get a liquid of technetium-99M, which is a short-lived isotope. It only has a half-life of 6 hours. And we put it on equipment. We'll put it on things that replicate the skin. And I'll tell you what, the first time I did it, I was actually, I was at CBRF and we came down here, and it was the first time it was done down here. And it spreads like wildfire. And it's crazy, especially in the kind of what's going on now in the world. You can't see it, and you don't know how far it's spreading, but your detection equipment sure can know. We had a lot of people that got contaminated, but the thing is, they're good. It's a low-level gamma. We act as if it's alpha because we'll spray it on areas, but in 3 days it's gone. So we usually will do that training in the middle of the time someone's here, and 3 days later they can just come and get their PPE that is pretty much now just salt water.
So yeah, I think Lloyd, Kerry makes a good point. I was the commanding officer of the Chem Bio Incident Response Force, and it is difficult. And a lot of times people don't know how to use their equipment because they've never experienced a live source. They've got somebody whispering in their ear, "Hey, now your device reads this." So working in that live environment is definitely useful. Training in that live environment is definitely useful. I can tell you that some of the venues, Guardian Centers being one of them, have the ability to create live radiation fields, and they can have the field get stronger as you get closer to ground zero and that sort of thing. So very, very useful and certainly worth taking a look at. We can provide you more information after the presentation. If you're interested, you can contact the HDIAC directly and we can help with that. So I think that's going to wrap it up for today. It's 12:55. I'd like to thank all of you so much for joining us today. As we mentioned at the beginning of today's webinar, the slides and recording of this presentation will be made available for download at our website, www.hdIAC.org. If you're interested in learning more about the HDIAC, you want to talk to Kerry one-on-one, or you're interested in getting involved as one of our subject matter experts, a presenter, or expanding your presence in our user community, you can feel free to reach out directly using the contact information that you can see there on the left hand of the screen. In addition to our monthly webinars, the HDIAC offers monthly podcasts that span the range of our 8 technical focus areas. We also put out a bi-weekly email digest that you can sign up for, and it presents the latest scientific and technical news in the Homeland Defense field. And we offer a technical inquiry service where you can submit a question and we'll give you up to 4 free hours of technical consulting and work to answer that question for you. If you're active in this community and you're interested in becoming a subject matter expert, please reach out. Our subject matter experts contribute in a variety of ways, like Kerry did today, presenting webinars, providing podcasts, or consulting as needed on technical inquiries that the HDIAC receives. Again, contact information in the chat box on the left-hand side of the screen. And be sure to join us on 6 May for our next webinar, where we're going to cover the National Renewable Energy Lab's Consolidated Utility Base Energy Hybrid Energy System. A very interesting presentation system that's able to take energy from a variety of sources and convert it to energy that's usable by military and disaster scenarios and those sorts of environments. So finally, again, thanks for your time today. I know time is a valuable commodity. It's precious to you. It's precious to us, and I hope you enjoyed today's presentation. Best regards, and to all of you, stay well.